Welcome back to the Cell and Molecular Biology course. As we have discussed earlier, the most important invention that led to the modern understanding of life at the cellular level is the invention of microscope. In this video, we will explore the light microscope in detail. Let's begin. What is a microscope? As we all know, a microscope is an instrument used to magnify small objects. The word microscope originates from the Greek word micro meaning small and copian meaning to view. Now let's see what is a light microscope. Light microscopy is a technique which uses visible light to illuminate and observe a specimen. The main features of light microscope includes magnification, which provides a detailed and enlarged image of the sample. The interaction with light reveals how samples absorb, reflect, and scatter light. Now, before we study the light microscope in detail, we will see a brief history of the microscope. In the 14th century, spectacles were first made in Italy. This marked the beginning of the use of lenses. In 1590, as we studied in earlier videos, the first microscope was invented. Apart from this, ancient Chinese texts also have mentioned viewing magnified objects through a water-filled tube. This could be an early form of magnification. Later in 1667, Robert Hooke publishes Micrographia, a groundbreaking work in microscopy. Here is a picture of microscope used by Robert Hooke. Later comes Leeuwenhoek's observation. He used a single lens microscope to observe bacteria and microscopic life forms. Here is an image of a replica of Leeuwenhoek's microscope. Later in 18th and 19th century, improvisations were made in microscopy. In 1830, Joseph Jackson Lister improved the magnification clarity by using weak lenses at varying distances. Using his improved lenses, he became the first to accurately identify the true shape of red blood cells in mammalian blood. Lister's lens system has greatly improvised the image resolution and have paved way for future invention of microscope. Let's move on to Abbe's theory. Abbe's theory was developed by Ernst Abbe in the 19th century. He explained the fundamental limits of resolution in microscopes. The theory actually describes how light passes through a specimen, interacts with the optical system, and then creates diffraction patterns that are critical for image formation. Abbe's sign condition helped optimize lens designs, minimizing distortions and improvising the image sharpness. His work laid the foundation for aplanatic lenses, which correct chromatic and spherical aberrations, leading to clearer and more accurate images. Let's move on to Kohellet's illumination. In 1893, August Kohellet developed a technique for even specimen illumination, which became a fundamental method in microscopy. This provided uniform and bright lighting across the specimen, allowing for high contrast and resolution without a glare. It works by using double diaphragms to focus light optimally on the sample while keeping the condenser and light source aligned properly. This method is still widely used in modern microscopes, significantly improving image clarity and detail. Now let's move on to the 20th century inventions and improvisations in microscope. In 1903, ultramicroscope was invented. Later in 1932, phase contrast microscope was invented. This actually allowed the study of transparent biological specimens without staining, and this is a revolutionary invention in cell biology research. Later, the electron microscope was invented by Ernst Reska and Max Knoll. In 1931, the first electron microscope was developed, but it had a poor resolution. Later in 1939, the first commercially available electron microscope was developed. This enabled observations at higher magnifications. Now let's move on to the light microscope in detail. Before entering the principles of light microscope and how they work, let's see the basic types of light microscope. As we all know, a light microscope can be a simple or a compound microscope. Let's begin with a simple microscope, which uses a single lens. An image of a simple microscope is shown at the left. The simple microscope magnifies objects 3 to 20x level, and it resolves down to below 1 micrometer. Simple microscope is used for dissection to observe development of a chick embryo and an egg, and also to see small animals like ant, bedbugs, etc. As we can see in the illustration below, a single lens is used to magnify the object. Now let's move on to compound microscope. Compound microscope is the one which uses multiple lenses in alignment. It can magnify up to 2000x. It resolves down to about zero point 0.2 micrometer. The compound microscope illustration is shown at the right. As you can see, a light source and a condenser lens which focuses the light on the specimen. The light is focused on the objective lens where you can view the specimen. Now let's see the parts of a microscope. Generally, a microscope has two subsystems, an illumination system and an imaging system. Illumination system is the one which provides light to illuminate the sample. In early microscopes, sunlight was used to observe the samples. It actually used the sunlight which is reflected by a mirror. In modern microscopes, we use artificial light sources such as light bulbs, LEDs, and lasers for reliable and controllable illumination. Now that the imaging system produces a magnified image from the light interacting with the sample. Light shaping and optical filtering. Light shaping ensures high resolution and contrast by controlling the illuminated area and light angles, while the optical filtering modifies light spectrum and the polarization to enhance specific features, improve weak signals, or observe fluorescence. All these were modified in the modern microscopes. Now let's see the general structure of a compound microscope. As you can see, a mirror at the bottom of the image. It is a reflecting mirror. It reflects light on the object. And then a condenser. It focuses light on the object. The condenser has a diaphragm. It allows the required intensity of light to pass through. Later you can see the stage. It is a platform with a hole at the center. The light falls on the object through the hole. The slide is placed on the stage. And you can see two stage clips which holds the slide firmly on the stage. And then the objective lens. It is a biconvex lens. It magnifies the object. And you can see the nose piece, which is a form of a rotating disc having holes for fitting the objective lens. Usually, objective lens of varying magnification are placed in the nose piece. Then you can see a body tube, which has eyepiece at the upper end and objective lens at the bottom end. As you can see, a coarse adjustment, it can actually move the body tube to adjust the distance between the objective lens and the object. And then you can see a fine adjustment knob. It moves the body tube up and down slowly to make exact focusing. And then you can see an arm. It supports the body tube and coarse adjustment. And the inclination joint. It is actually used for tilting of the upper part of the microscope to while setting the level of the eye. And you can see the base or foot at the bottom. It actually gives support and weight to the microscope. Now let's see the basic function and the principles of light microscope. The basic function includes the focusing of a beam of light through a transparent specimen to create an image. The image is magnified using one or more lenses for clearer viewing. Moving on to light refraction. Light refracts or bends as it passes through different mediums depending on the refractive index. This bending is essential to focusing light on the specimen. Now let's see lenses and focusing. Convex lenses focus the light at a specific point known as focal point. The shorter the focal length, the greater the magnification. Microscope lenses work by bending light at precise angles to focus on tiny details. Moving on to the resolution, the microscope's resolution defines its ability to distinguish between two objects close together. The resolution is dependent on the numerical aperture and the light's wavelength. Now let's see the magnification. Magnification is the process of enlarging the appearance rather than the physical size of an object. This enlargement is measured by a value known as magnification. Compound microscope uses two lens system. As we have seen earlier, the objective lens and then the eyepiece lens or ocular lens. The objective lens magnifies the specimen and projects a virtual image into the body tube. The ocular or eyepiece lens further magnifies the image from the objective lens. The magnifying power is calculated using the formula size of the magnified image divided by size of the original image. Now let's see the steps used in viewing a slide. First, we have to obtain a slide and clean it. Then we have to check the ocular and all objective lenses if they are clear without any dust. Then we have to use the coarse adjustment knob to obtain maximum working distance. Later, we can place the slide on the stage. The slide should be fitting into the slide holder. As we have seen earlier, the slide clips should hold the slide in position. Use the stage adjustment knob to move the slide over the aperture in the stage, which is the hole through which the light is focused from the light source. Later, we can rotate the lower objective lens into the place, and then by using the stage adjustment, we can position the slide until the area of interest is centered for examination. Later, we can rotate the higher power objective into place and observe the sample. Using the fine adjustment knob, we can sharpen the focus. And we can also adjust the diaphragm lever for optimal lighting. For oil immersion, we have to coat the specimen with transparent oil and then observe using the oil immersion lens, which has increased resolving power. When we have finished observing the specimen, we have to use the course adjustment knob to maximize the working distance and then remove the slide. Then we have to return the microscope to storage. Let's move on to the procedure for cleaning a microscope. Before cleaning a microscope, we have to turn off the light and then we have to use the course adjustment knob to obtain a maximum working distance and then remove the slide from the stage. Then we have to use a tissue paper to clean all the lenses. We can use 70% ethanol to clean them. Later we can rotate the scanning objectives into place and ensure the working distance is set. Moving on to the microscope safety cautions. We have to always hold the microscope in an upright position by holding the arm with one hand and supporting the base with the other. Always focus using the lower power objective lens first before switching it to the higher power objective. We should never remove the slide while the higher power objective lens is in position. We have to make sure that the lower power objective is back in viewing position before removing. We have to clean the stage and lenses with tissue paper after use and then store the microscope in a cabinet after usage. As we have studied the principle and working of the light microscope, let's move on to the types of the light microscope in detail. The types include bright field microscope, dark field microscope, phase contrast microscope, differential interference contrast microscope, fluorescent microscope, confocal microscope, and ultraviolet microscopes. Let's see each of it in detail. Let's first see the bright field microscope. It is also known as a compound light or bright field microscope. The bright field actually is one of the simplest microscope. Despite this, they can blend well with the new technologies, including digital imaging systems. The bright field microscope actually uses light rays or beams to create dark images against the bright backgrounds. Bright field microscope can be used in cellular biology and microbiological lab studies. They are often used to view live cells or fixed specimens. As many organic specimens are opaque or transparent, staining is necessary. This will give them enough contrast to be visible under the microscope. We can use different staining techniques and stains depending on the kind of cell structure and specimen we are examining. Moving on to the dark field microscope, also known as dark ground microscopes. These microscopes have special condensers that will scatter light and then cause it to bounce off specimens at a specific angle. Accordingly, specimens have dark backgrounds in dark field microscopic images. This microscope is best for extremely small live specimens and for viewing liquid samples, finding cells in suspension. Let's see phase contrast microscope. These microscopes transform phase shifts in light passing through transparent specimens into brightness and then changes into images. They are often used to create high contrast images of transparent specimens, such as microorganisms, thin tissue slices, and other subcellular particles. These microscopes have dozens of applications, but they have most useful in observing colorless, transparent, and unstained specimens. In the right, you can see differential interference contrast microscope or DIC, or you can also call Nomarsky microscope. These microscopes introduce contrast to images of specimens with little to no contrast when viewed through bright field microscope. This microscope uses a beam sharing interference system to produce monochromatic shadow cast images that specifically shows the gradient of optical paths for low and high spatial frequencies. DIC microscopes produces high resolution images with fog 3D effects. Fluorescent microscopes are used in multiple fields to gather images of smaller specimens, such as cells. The technique is that samples are treated with fluorophores so that they can re-emit the light after being excited by a light source. We can then use the light source to reflect light at desired emission and excitation wavelength. As a result, we can obtain the high resolution image. In the right, you can see a confocal microscope illustration. The aim of this microscope is to increase optical resolution and contrast by using a spatial pinhole to block out of focus light. These microscopes can be used for time-lapse imaging, visualizing and analyzing subcellular biomolecules and structures in live and also fixed specimens, such as proteins. And it can also be used for fluorescence recovery after photo bleaching and then FRET, Foster resonance energy transfer. And the other type of light microscope is the ultraviolet microscope. These microscopes use ultraviolet light as illumination. They use shorter wavelength than the visible range to provide greater magnification than ordinary optical microscopes. They are used in forensic science, quality control, and contamination detection in pharmaceutical industry, and also in nucleic acid detection and DNA RNA quantification in biology. Each light microscope type offers different benefits. The light microscope revolutionized biological research, allowing scientists to explore micro world in ways which were not possible before. Understanding how light interacts with lenses have paved the way for groundbreaking discoveries in biology and medicine. From early designs to modern advancements, the light microscope remains an essential tool in scientific discovery, continuing to shape our understanding of the living world. Thank you. Hope this video was useful. See you in the next video.